Welcome back. In the previous lectures, we have started doing Fourier analysis on real line R, and we have assumed our function to have a moderate decay in the sense that f of x modulus is less or equal to some constant times by 1 plus x square. Now, what we have seen is that f hat is defined through e to the power 2 pi I j x. So, this is just to write the notation f hat at xi, this is equal to minus infinity to infinity f of x e to the power minus 2 pi I x xi dx. This is for xi, and then what we have seen is that f hat of xi is less or equal to some constant, that means f hat is a bounded function, and f Riemann-Lebesgue lemma says that f hat of xi goes to 0 as mod xi tends to infinity, and we are assuming f to be continuous, then actually f hat is also continuous. In other words, f hat belongs to C 0 of R, set of all continuous function which vanishes at infinity. Okay. So, today we would like to address the question that what is the resemblance of this Fourier transform vis-a-vis the Fourier series. Suppose, for example, in particular if we take f to be a function which is supported on minus pi to pi, then what is the kind of the relationship between the Fourier transform and the Fourier series. So, can we recover some of the result by using the Fourier series techniques. Now, towards that end, let us have a toy example. So, let us take our f, let f be a continuous function with compact support that is and support of f is contained in some minus n to n in some interval. That means, f is a continuous function if you have minus n to n. So, outside this interval this is going to vanish 0, and here it is a continuous function. So, this is outside certain finite interval, this is 0, and so let us assume f hat of xi is less or equal to some constant by 1 plus mod xi square. That means, both f being a continuous function obviously has moderate decay, and on top of that we are assuming that f hat also has moderate decay. So, now for any L greater than 0, define a n of L, this is equal to 1 by 2 L integral minus L to L f of x e to the power minus 2 pi I n x divided by 2 L dx. So, now if remember that if we have a 2L periodic function, so this is going to be the Fourier coefficient of that 2L periodic function. So, now we have if L is greater than n, then this I can represent in terms of the 2 pi periodic 2L periodic function, and hence we can get that A n L, this is equal to f hat of n by 2L. So, as we know that 1 by 2L factor. So, here as you can see, because we are assuming that f hat has a moderate decay. So, summation over mod of f hat of n by 2L, this is finite. Therefore, the Fourier series is an absolute summable series and it converges to a continuous function at every point. That is what we have learned from our Fourier series course. So, then we can write f of x, this is equal to summation over a n l e to the power 2 pi I n x by 2L, which is equal to 1 by 2L summation n. We can write actually summation n from, we can take it from minus infinity to infinity, and f hat of n by 2L e to the power 2 pi I n x by 2L. We have already assumed that f is a continuous function, and so now let us try to look at what is the meaning of n to n f of x dx. Now, this that means I am taking minus n to n. The meaning of this is that we will take a partition. This is 1 over n. So, this is actually all this partition is 2 n over n. So, and so take the partition x j minus n is equal to x naught is less than x 1. So, which is going up to x n, which is equal to n. This is what the partition we have taken. So, therefore, this Riemann integral can be approximated by a Riemann sum. So, what is the Riemann sum? Riemann sum would be 1 over n summation over j from 0 to n f of minus of n plus 2 n j by n, each one is 2 n by n. So, this I can always rewrite this as 1 over n summation over k is equal to minus capital N n to n n f of k by n. So, this is going to approximate as n goes to infinity, this is going to approximate the integral above integral minus n to n. So, therefore, that is what we will write minus n to n f of x dx, this is equal to limit n goes to infinity 1 over n, I can write that this is n n f k by n. So, therefore, minus infinity to infinity f of x dx, this is equal to limit n goes to infinity. So, this we can write that n goes to infinity 1 by n summation k is equal to minus infinity to infinity f of k by n. This is true for any continuous function. If f continuous, then this we can write for every continuous function. So, therefore, if I take my f in particular to be minus infinity to infinity f hat of xi e to the power 2 pi I x xi d xi. You see, we are assuming f hat to have moderate decay. So, we can define this integral as limit n goes to infinity minus n to n of this function. So, this by our previous observation in terms of this f, if we are taking f hat of xi e to the power 2 pi I x xi d xi, then this tells us that this is limit n goes to infinity 1 over n summation over k from minus infinity to infinity f hat of k by n and e to the power 2 pi I xi k by n. And this what we have seen is that this is going to be nothing but what we get is that this is f of x in our previous observation. So, here this is essentially what we are trying to do is that we are getting some sort of the Fourier inversion if we are assuming f and f hat they are nicely behaved moderate decay through by converting the problem into the Fourier series and then we are getting it back. Now, one of the fundamental tool while dealing with the Fourier series either in the circle or for finite abelian group, we have exploited the convolution of two functions a lot. So, it is now assume both f and g have moderate decay and continuous. Let us take, then define f convolution of g at x, this is equal to minus infinity to infinity f of x minus y g of y dy. Look at that this integral exists because both f and g they have moderate decay. So, now in particular they are bounded. So, if you push the modulus inside, then you can pull out the bound for g or f, then mod of g is integrable. So, there is absolutely no problem in defining this integral. Now, this also by the change of variable with the Riemann integration what we have seen, I can write that this is g of x minus of y dy, that in a sense is also you can write it as g convolution of f at x. Now, both f and g they have moderate decay. Now, one would like to ask this whether this function f convolution g also has moderate decay or not. So, now in order to see that we need to get f convolution of g at x. So, this is lesser equal to integral minus infinity to infinity mod of f of x minus of y mod of g of y dy. Now, I break this integral into two parts. This integral is mod y is lesser equal to mod x by 2 mod f of x minus of y mod g y dy plus integral mod y greater than mod x by 2 mod g y dy. Now, look at for the first integral, let us name them 1 plus 2. Now, for 1, now mod y, as you can see that mod y is lesser equal to mod x by 2. Now, mod of x minus of y, this is greater or equal to mod x minus mod y. Now, minus of mod y is greater or equal to minus of mod x by 2. So, this is greater or equal to mod x minus mod x by 2, which is equal to mod x by 2. Therefore, mod of f of x minus of y, this is going to be lesser equal to, as f has moderate decay. So, what we are going to get by a mod of x minus of y square. Now, mod of x minus of y is greater or equal to mod x by 2. Therefore, this is lesser equal to a by 1 plus mod x square by 4. So, this definitely is lesser equal to some constant divided by 1 plus mod x square. So, so the mod of I is lesser equal to some constant b 1 plus mod x square to minus infinity to infinity mod of g of y dy, which is a finite number and which is independent of x. Therefore, the first part we can see that it gives the moderate decay. This is what we are getting for the first part. Now, let us look at the second part. Now, for the second part, mod of y is greater than mod x by 2. This is already given. So, now I will use the moderate decay of g. So, this is lesser equal to some constant by 1 plus y square, and now this is lesser equal to again b by 1 plus mod x square. Therefore, 2 is lesser equal to b by 1 plus mod x square into integral minus infinity to infinity mod of f of x minus of y dy. By making a change of variable, we know that this is equal to 1 plus mod x square integral minus infinity to infinity mod of f of y dy, which is again independent of x. Therefore, what we have got is that the second is also giving us the moderate decay. Therefore, so in conclusion, we have f convolution of g at x modulus is lesser equal to some constant by 1 plus mod x square. Now, one would like to ask that what about if I have a convolution, so which has a moderate decay. So, I can talk about the Fourier transform of that convolution and what is going to be the Fourier transform of this f convolution g in this case. In the case of the circle, what we have seen is that f convolution g hat at n is f hat of n into g hat of n. The similar result holds true in the setting of finite abelian group. Now, in this case also this will be standard. argument f convolution of g hat at xi, this is minus infinity to infinity f convolution of g of x e to the power minus 2 pi I j x dx, which is equal to minus infinity to infinity, and then I will open up the f convolution of g. This is f of x minus of y, g of y dy e to the power minus 2 pi I j x dx. Now, both f and g both have moderate decay. The modulus of f in times the modulus of g, they are the finite. So, integral is finite. Therefore, I can interchange the order of the integration. So, the moment we change, so we have got infinity. So, this is g y minus infinity to infinity f of x minus of y. Here I will put minus 2 pi I j x minus of y dx. Now, extra factor I am writing is e to the power 2 pi I j y. So, I need to cancel that, and then this is dy. By making a change of variable for the inner integral, we have f of x e to the power minus 2 pi I j x dx, then e to the power minus 2 pi I j y dy. This is equal to minus infinity to infinity g of y e to the power minus 2 pi I j y dy, and heated with f hat of xi, because the inner integral is going to give us f hat of xi. So, this is nothing but f hat of xi g hat of xi. So, that is also true. Now, we have both f and g, they are continuous function. Therefore, exactly following in the same fashion, it is one can show that f convolution g is also continuous, exactly the way we have proved in the case of the circle or 2 pi periodic function. So, what you can do is that f convolution of g of x minus f convolution g of y, this is equal to minus infinity to infinity f of x minus let us say s minus f of y minus of s, and then g of s ds the mod. Now, what one does is that if x is close to y, then what we need to show that this one is small. So, this is lesser equal to minus infinity to infinity mod of f of x minus of s minus f of y minus of s mod g s ds. Now, if f given to us, if it is uniformly continuous, then we can use that if x is close to y, then f of x minus s minus of f of y minus s will be less than epsilon. So, what we know that by continuity, for epsilon positive, there exists a delta greater than 0 such that mod of f of x minus of s minus of f of y minus of s is less than epsilon whenever mod of x minus of y is less than delta. But as you can see that here the integral here for every s I can my delta s delta can depend on s. So, if instead if we have the uniform continuity, then definitely we could pull out the smallness of the difference outside the integral, then we will be left with minus infinity to infinity mod of g s ds. So, this says that what we need is the uniform continuity. Now, we have only we are assuming that f is a continuous function and with a moderate decay. Now, if f has moderate decay, you can easily see that f of x, which is less or equal to a by some constant x square, and this goes to 0 as x goes to mod x goes to infinity. Therefore, now this function is a continuous function, although and around infinity this is what is happening is that it will be it goes to 0, that means f if continuous, then this is C 0 of r. Now, f so now here what you can say is that mod of f of x is there for epsilon positive, there exists a r greater than 0, this is less than epsilon whenever mod of x is greater or equal to r. Now, outside this, outside minus r to r, we have 1 epsilon, it is less than epsilon. So, we do not need to bother about the tail part of the function, that is itself is giving the uniform continuity. And now, what we are left with? We are left with minus r to r, and this is a compact set. So, f is continuous, hence if I look at f as a map from minus r to r, then this restriction will be uniformly continuous. So, f is uniformly continuous. Therefore, I can pull out the smallness of f from this integral without having any problem, and then thus we get f convolution of g of x minus f convolution of g of y is less than epsilon times minus infinity to infinity mod of g of s ds whenever less than delta. So, we can choose our epsilon, because instead of epsilon, if we want to work epsilon by minus infinity to infinity mod g s ds, then this will give the smallness. Anyway, this is a finite integral minus infinity to infinity mod g s ds is a finite number, and I can choose my epsilon to be small, so that this is. So, this also says that with assuming the continuity of f and then f convolution g, if both have moderate decay, then f convolution g is also a continuous function. Okay. So, now to draw the analogy further, So, there what we had seen is that the fair kernel was extremely important for us to study Fourier series, and it is natural to ask what is the equivalence of fair kernel here. Thank you. We will discuss this in the next lecture.